Welcome to the year 2030. New lasers are being used to observe the movements of electrons. People know at last how the elementary particles behave under different conditions. They can monitor and even control them. In medicine, people have also developed new laser techniques to diagnose diseases at an early stage which used to be incurable, like cancer and Alzheimer's. The new pictorial processes permit us to look inside a cell and to recognize early molecular changes within the molecules. Conventional microelectronics has long been replaced by the much faster light-wave electronics. Information is now 1,000 times faster than it was 20 years ago. This could one day be the result of the research by Ferenc Krausz at the Max Planck Institute of Quantum Optics in Garching. He is investigating the movements of electrons within the atom and wants to photograph them. He is, so to speak, the electron paparazzo. Everything around us consists of tiny atoms, but what do atoms actually look like? They consist of positively charged protons.
Hello.
And neutrons.
Hello.
And of course electrons. For Ferenc Krausz, these are the stars in this constellation, and they are negatively charged. The electrons circle round the nucleus. When atoms join together, they form molecules. These then share their elementary particles, their stars. They use the same flight path. These are also known as orbitals. This is how chemical compounds and all molecules are formed. The scientists track down the electrons using lasers. Ferenc Krausz and his team photograph what is happening inside the atoms using ultra-fast laser flashes. Because electrons are extremely active and move incredibly fast, in this world of quantum physics, movement occurs erratically. Electrons can react to light. If light encounters an electron, the latter can absorb energy. It leaps into a higher orbital. When it falls back into its original orbital, it releases the energy it has absorbed in the form of a light particle known as a photon. These movements occur within attoseconds. That is a billionth of a second. At least in theory. But is that really true? Scientists want to make these movements visible. Until 10 years ago, this was impossible.
We want to know what happens when electrons go on a journey. How long does it take for them to leap onto their orbital within the atom? How fast do they move within the molecule, or in the smallest microelectronic structures? That's the aim of attophysics.
But the movements of the electrons are extremely fast. Physicists can only observe their behavior if they can develop camera shutter times which are just as quick as the particles leap. If they are too slow, the object will have already disappeared from the picture or will be blurred. The shorter the flash, the more precisely movements can be observed in focus and without distortion. That is what they are aiming to achieve. For the scientists, that means flashes of light lasting for only attoseconds. That is a figure with 18 figures behind the decimal point. That is precisely the time that Ferenc Krausz needs to record the movement of electrons. The challenges they face can be divided into two phases. Phase 1, generate flashes which are only attoseconds long, a succession of ultra-short flashes, 3,000 per second. But how could this be achieved? Until recently, the shortest laser pulse which could be produced was 1,000 times longer than an attosecond. Then he had an idea. It might be possible using a specially built attosecond chamber.
We used to be far too slow, and we virtually always missed the electrons. So we had to generate shorter pulses in order to be able to capture them. The idea was to take laser light flashes produced by a single strong wave. If we fire light pulses like that at atoms of noble gases, the most weakly linked electron within the atom will be torn away from the atom by the strong field. A few moments later, the direction of the field changes and hurls the electron back into the nucleus of the atom once more. At that very moment, the electron gives up its energy and emits an attosecond flash.
Put simply, that means the electrons themselves ensure that it works. An electron is accelerated by the laser light and is briefly catapulted out of the atom. As it falls back in, it emits light again, within a period of attoseconds. Success! Now the scientists have succeeded in making the shortest pulse which can be created with a laser even shorter. At the moment, Ferenc Krausz holds the record at 80 attoseconds. It won him an entry in the Guinness Book of Records, and it makes him the world's fastest photographer.
Not only did we have to generate the flash, that was only the start. We want to conduct experiments with the flashes as well.
Now for phase 2. The experiment. The attophysicists want to know what happens when an electron is shot out of a krypton atom. They fire different light flashes in succession at a sample. In doing so, they shoot an electron out of the atom. The attosecond flash then photographs the movements of the remaining electrons. You can imagine it this way. Light is both a wave and a particle, and energy. The bowling ball represents the light wave and light particles. The aim is to hit the electrons. Only when they are actually shot out will they leave an empty space in the structure. The result could be that the distribution of the load within the atom changes, because now the negatively charged electrons are missing. And what exactly happens at the place from which they have been ejected? The physicists were able to answer this question as well. With this experiment, they succeeded for the first time in recording processes taking place deep inside an atom. With the aid of light, we can study the fastest processes in nature.
We can observe the movement of a hollow space inside an atom within attoseconds. And we can see that this hollow space moves extremely fast. It seems very strange to our everyday understanding that even a void can move. But that is precisely what we can see in this experiment.
Light is the only power which can change its direction as fast as electrons can move their positions. And this is how, in the 21st century, light has become a tool for medicine, biology, and information technology.
Through a better understanding of the microscopic movement of electrons, one day we shall be able to develop substances, new and more effective medicines, to understand better how diseases occur, and to make electronics which are several hundred times faster than those of today.